the reactions of alcohols. All right, we're gonna be really looking at this. Is everybody here? Everybody's attentive. Everybody's ready to begin.
Yes, sir.
Okay. No, alcohols are really interesting. Um, my favorite organic, one of my favorite organic molecules, obviously, right? The Caribbean's #1 organic molecule. So we're going to be looking at them. We're going to be looking at their structures, their characteristics, especially their solubility, and the level of alcohols that exist, right? And then different reactions that alcohols undergo, right? So let's have a look at them. Now, our objectives now. Whoa, give me a moment. Let me fix that immediately. Saw it. You see, I need to stop making PowerPoints early in the morning. All right, so learning objectives, right? So we're gonna be looking at some things that you need to know, right? On the completion of this general PowerPoint, you must be able to describe the reactions of alcohols with potassium permanganate, right, and potassium dichromate, right? Must. You must be able to describe the reactions of alcohols with carboxylic acids, reactions of alcohols with sulfuric acid, and describe the iodoform test, right? So I know that you guys have seen that before, right? I've seen all of them before. So we're gonna be looking at that per se, right? So let us start there. No, alcohols are called, or otherwise called as alkanols, right, are classified in a similar system that we'll see across all of organic chemistry, right? The general formula is CnH2n plus 1OH, right? And they may be classified according to the position of the hydroxyl group, right, um, on, the molecule itself. So if the hydroxyl group is attached to a carbon which is only attached to another alkyl group, it is a primary alcohol, right? If the hydroxyl group is attached to a carbon that is attached to not one but two alkyl groups, it is secondary, right? And if it's attached to a carbon is not that is attached to an alkyl group, right? Not only one, not only two, but three alkyl groups, it is tertiary, right? So that makes sense, right? That should make some sense, all right? So everybody is fine with that?
Sir, can you repeat it again, please?
All right. So if the OH group is attached to a carbon atom, which is attached to only one other carbon atom, it is primary, all right? So looking at these diagrams right here, so this is primary, right? So the hydroxyl group here is only attached to a carbon that is only attached to another carbon there. All right, so it's attached to a carbon that is attached to only one other carbon. Notice it's only attached to two other hydrogens. It's only one other R group it's attached to. All right, so it's primary in that case. All right. For secondary alcohols, right, it's attached to a carbon, which is also attached to two other carbons. So it's secondary. And when the hydroxyl group is now attached to a carbon that is attached to three other carbons, it's tertiary. So it's basically speaking to the amount of alkyl groups that are attached to the carbon bearing the hydroxyl group, right? That's what it's all about. Is that a little bit better? A little bit clearer?
Yes, sir.
All right, lovely. All right, let's move on. So the solubility of alcohols are important. The hydrogen bonds are formed, right? So we're looking at this. Hydrogen bonds are formed between water and alcohol molecules, which make alcohol soluble in water, right? So what we're looking at here is the fact that the hydroxyl group is polar, all right? And I realized I did not, add that there. Okay, and then you'd have to have a comma there before the does. All right. So hydroxyl groups, right, are polar. Let me fix that. Yeah, man. All right, so are polar. Thus, the hydrogen bonds, right, are formed between them. So you know how hydrogen bonds are formed from Unit 1 chemistry already. Not that should not be a problem, right? So we have that there. We have the formation of hydrogen bonds that allow for alcohol molecules to be flanked on multiple sides by water, right? To have it being solved, right, into the solvent, creating the solution, right? However, the alkyl group attached to the hydroxyl group is hydrophobic in nature, right? So it's nonpolar, therefore it's hydrophobic, right? Thus, the solubility of alcohols decreases with the increase in the size of the alkyl group, right? Low mass alcohols are soluble in water. So if you look at something like ethanol, right, which some people drink on a daily basis in different solutions and with different esters mixed into it, right, to give it different flavors. Um, Ethanol specifically is a low mass alcohol, right? So the alkyl groups here, this is its alkyl group, right? Only a two carbon chain. Really simple because it's ethanol, right? But if we look at something like decanol, 10 carbons, right? If we look at some things like that, octanol, right? So if we look at large alcohols like that, they will not be um, soluble in solution. Even butanol isn't that soluble, right? Because if we look at this, we have an ethanol solution like this, so it's dissolved. Then we have a propan-1-ol solution here, which dissolves. But notice that butan-1-ol does not dissolve correctly. So notice that it has like a surface there. So butan-1-ol, right, as it reaches around 4 carbons in its chain, it starts to, decrease drastically in solubility, right? And we have here an isomer. What type of isomer is this of ethanol? What type of isomer of ethanol is dimethyl ether? Can anybody tell me?
Sir, repeat your question.
What type of isomer to ethanol is dimethyl ether?
Is it an optical one?
No, 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 no. No, 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 no. Okay, so that tells me, So if we finish everything here, we're not moving on, We're going to isomerism next. All right. Thank you for letting me know. So what type of isomer to ethanol is dimethyl ether?
Structural. Oh,
No. Moving on. I'm sorry. But yeah,
sir,
if not,
answer a question. Can I not understand what you try to ask now? The
okay. Okay, somebody else said something I'll repeat. Meaning that both of them are isomers. What type of isomers are they? That's the question. Dimethyl ether and ethanol are isomers. What type of isomerism do these molecules exhibit?
Sir, someone said functional isomerism.
Okay, Faith said functional group isomerism, which is correct. Ding, 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 correct. Right? So same thing like esters and carboxylic acids, functional group isomers. Right? So they are functional group isomers here. So we have that wonderful. So ethers tend to be less, soluble than alkanols, by the way, just saying. And it's very evident by the structure. All right, so we have this here, the solubility of alcohols. Now, how do we distinguish between these alcohols now? Because we here, so we have primary, we have secondary, and we have tertiary alcohols. What are some of the tests that we use to distinguish alcohols?
Lucas reagent? No, Lucas test.
Lucas test, wonderful. Any other test?
I think there's one where you use potassium permanganate, I think.
Okay. Any other test? Anybody ever heard of Jones reagent? Jones test?
No, sir.
Right. So distinguishing between alcohols. Let's look at this Jones reagent. Acidified, right? Potassium dichromate. Right? So the Jones reagent is acidified potassium dichromate, right? And here we have now, if we have a primary alcohol, it will turn from orange to green. If we have a secondary alcohol, we will have orange to green. And if we have a tertiary alcohol, no observable change. All right. So we can distinguish between primary and secondary alcohols and the tertiary alcohol. Right. So the primary alcohols are oxidized to aldehydes, then to carboxylic acids. Primary alcohols are oxidized to aldehydes when the oxidation, so the oxidizing agent rather, is not in excess and the acid is fairly dilute. And when the aldehyde, and the aldehyde is distilled off immediately, right, due to its low boiling point. Now, aldehydes, ketones, alcohols, they're volatile, right? When we start talking about looking at hmm not the Beer Lambert's law. Why my brain went straight to Beer Lambert? When we start looking at Rolt's law and those type of stuff, we'll speak about the volatility of organic compounds, right? But we know that they're volatile, meaning that they're easily evaporated. Because when you smell acetone, it's really strong. When you smell alcohols, it's really strong. That means that their molecules easily exist in a equilibrium that gives a lot of you know what would I say now, evaporated particles. So if we're going to be adding heat or adding acid to them, right, we need to be able to distill off the aldehyde if we want to keep the aldehyde. So we only get aldehydes from the oxidation of alcohols, right? If the oxidizing agent is not in excess and if the acid is dilute, right? And if we make an attempt to distill the aldehyde, all right? The primary alcohols are oxidized further to carboxylic acids when the oxidizing agent is more in excess, right? And if the acid is concentrated. And also, if it is carried out under reflux for 20 minutes. Now, do you guys know what reflux is? Can anybody describe what reflux is? Give a description of what reflux is. All right, I'm not hearing anyone. All
Sir,
right,
when you said redox, right?
reflux.
Oh, reflux. Reflux is like constant boiling and cooling. You could like set up reflux apparatus where there's like some steady inflow of cool water, and you're heating something under it so that when the rate of evaporation increases and there's a lot of evaporation, it could all cool down and drop back into the liquid to be continuously boiled again.
Okay, wonderful. So that's what reflux is, right? We're going to be looking at that. But let's have a look at ethanol, creating ethanol from ethanol, right? So in ethanol, right, how we get ethanol is by the oxidation of the alcohol itself. So we oxidize the alcohol within an acidic media, right? We add heat in order to, increase the rate of reaction, kinetic theory. Everybody would know that, all right? And then what will happen here is that we have the acidified potassium dichromate here, right? And we're having that reaction happen under gentle heat, right? And then as the aldehydes, the ethanol evaporates and goes up, right? We distill it off and it goes in here, right? So as the distillate, all right? So we have here the ethanol being sloughed off. So using acidified potassium dichromate or permanganate, right? Primary alcohols are oxidized straight to the carboxylic acids, right? Using modified setups, right? Under reflux, we get carboxylic acid, and under distillation, we get aldehydes. The reason why I'm doing this so much and telling you guys difference so much is because difference is important, right? So really, really important. So we have that there, right? So the orange dichromate ions turn green as they're reduced to chromium 3 plus. And we understand all of that as we went through module 3 already in unit 1, and we understand the colors, right? And the oxidation states of our transition elements, right? And we know that transition elements are normally used as catalysts. Okay. So we have this here, the creation of ethanol from ethanol, right? Here now we have something a little bit different, right? So I tried my best to find reflux gear a little bit better, right? But this is what a reflux apparatus really is, right? So as the person was, oh, why did I forget? um the name, as Nicholas was describing, right? This is a reflux apparatus. So in this diagram in which you had like an area for the aldehyde to escape, in this case, no, the aldehyde is going to be evaporating up, and in the cooling jackets, right, it's going to be cooled down and re-enter the solution, right, where the aldehyde will be further oxidized into carboxylic acid, all right? So we have that there. Everybody understands that? Everybody's fine with that?
Yes, sir. Now, could you go it over one more time?
All right. So we're going to be heating the solution of, in this case, it is propan 1-ol. Let's just say use another alcohol, right? Propal 1-ol, right? So we're going to be heating the propan 1-ol in the presence of an oxidizing agent. Oxidizing agents are denoted by this, right? So it could be a permanganate or a dichromate. Wonderful, all right? So it's going to, in this case, it will be the dichromate, just because of the color of the solution. It's dichromate, right? So we're going to be breaking them down. We're going to be oxidizing them. We're going to oxidize our propanol, which has a boiling point of 97 degrees Celsius, to propanal, which has a different boiling point. And we know that's how distillation works. It's because the boiling points are different, right? So as the propanol, which is more volatile, evaporates out, right? What we'll do if we want the propanol, right? What we'll honestly do is actually just, distill it off. But in this apparatus, we don't distill it off, right? We allow for a cooling jacket to be placed, right? So what's happening here is that cold water is running all around this film here, and that will condense the aldehyde, the propanol. It will condense the aldehyde and it will drip back into solution, right? So it's going to drip back into contact with the oxidizing agent, being further oxidized from propanol to propanoic acid. Make sense?
Yes. Yes, sir.
Wonderful. Lovely. All right. So let's look at this. This is what we're happening in the Jones reagents now, right? The potassium dichromate Jones test. Propan 1-ol is a primary alcohol. Let's draw propan 1-ol, right? Um, propan 1-ol, right? Really, really simple, right? What is propan 2-ol? Propan 2-ol is going to be something like this, OH. Let me draw them over their specific area. So propan 1-ol. Do you guys, never mind, let me not give you the option, because if I give you the option, you're going to give me the easiest option. Right? So we have propan 1-ol there. Here we have propan 2-ol. And now we need 2-methylpropan 2-ol. What is that now? How would we describe that now? I'm going to draw it in a structure like this, by the way. CH3, right? That is it, right? So the tertiary alcohol here, 2-methylpropan 2-ol, right? Really simple. So we have these different ones now. Note that this is primary because it's only attached to a carbon that is attached to only one other carbon, so it's primary. Here in the propan 2-ol, it's attached to a carbon which is attached to two other carbons, which is secondary. And here in the 2-methylpropan 2-ol, it is attached to a carbon which is attached to one, two, three other carbons. This is tertiary. Any questions, issues, anything happening there? Any issues there?
No.
No? All right. Remember, if there's a question, you just ask, no matter what the question is. Right? So we have the primary alcohol, right, being oxidized, right? And then we have the secondary alcohol being oxidized. But the tertiary alcohol is not oxidized. It just remains like that. It's just fine by itself. Right? So we have that there. So just looking at this now, the alcohol oxidation patterns, right? For primary alcohols, they're oxidized, right, to give aldehydes and then give the acids, right? The carboxylic acids. For secondary alcohols, right, they're oxidized to give ketones, actually. They oxidize to give ketones. Do you guys understand that why it gives ketones? Do you guys understand why it gives ketones? Okay. Am I moving a bit too fast?
No, sir. We just
Or
never learned that part. We just
ah,
know that turn ketones tertiary have no reaction, how primary turn aldehys and carboxylic. We don't really know why.
oh, crazy stuff. All right. So what we're gonna look at, right? What is oxidation in terms of hydrogen? Let me ask that. What is oxidation in terms of hydrogen?
The loss of hydrogen.
Wonderful, right? The loss of hydrogen. So if we have if we have propanol, right? Let me just use propan one all. No, something simpler. Ethanol, right? So let's just use ethanol. So we have ethanol like this. Then I would have to use propan one all for the next one, right? If we say that the thing is oxidized, right? Isn't it losing its hydrogen? So the hydrogen is going to be removed from the compound specifically, right? Like that. So it's going to be removed, right? And then another hydrogen is going to be removed, giving a double bond to an oxygen, right? So when we're oxidizing alcohols, two hydrogens are going away, giving a double bond to an oxygen there, right? And that gives us the aldehyde functional group. This is ethanol. But if we have prop, right? I'm gonna draw it a little bit weird, so because I need space to actually do these things. All right, let me just drop the hydrogen there. Propanol will give us the same thing. If we remove the two hydrogens, right, both of those disappear. We're going to get the double bond there, aldehyde. All right. But let's say that we actually have a secondary alcohol where this hydroxyl group is here, right? We're going to be removing two. Give me a moment. Let me just go back. We're going to be removing two of the hydrogens, right? Giving rise to a double bond there on the center of the molecule. This is a ketone, right? So depending on where the hydroxyl group is, right, then we'll have a different reaction. And isn't that the same thing that we understand from this? If it is primary, it will give us an aldehyde because the carbonyl group will be formed at the end of the chain because it's primary. Secondary, the carbonyl group will be formed within the chain, so it will give us a ketone. It is secondary. Make sense now?
Yes, sir.
All right. Because I don't want you to just know, because knowing is never the issue for CAPE students, right? So they tend to try to know everything, but understanding is much different from knowing it, right? So understanding where we're coming from. For tertiary alcohols, they cannot be oxidized regardless of the oxidizing agent. They just don't oxidize, right? The hydrogen is a must, right? It must be there, right? We can't move anything. We can't do anything to it. It must remain in its state, right? It must remain there for the stability of the compound, right? So no reaction there for the tertiary alcohols, right? So looking at that now, so that's the reactions with potassium dichromate. Now let's have a look at the iodoform test now. The iodoform test, the iodoform reagent is iodine suspended in alkaline medium. All right. So usually the alkaline medium that we use is something that's some basic salt, right? That tends to be, well, I wouldn't use that. Well, some basic compound. Let me not say salt, but basic compound, right? That tends to be really cheap and really accessible. So it's sodium hydroxide in this case. And with primary alcohols, only ethanol would give a positive test. No other primary alcohol can give a positive test in the iodoform test, but ethanol. So if you have a positive reaction here, it is only ethanol or it is a secondary alcohol. If not, it could be a primary alcohol that is not ethanol, or it could be a tertiary alcohol. That is the result of our iodoform test. Go ahead.
Sir, could you re-explain the test again?
Okay, I'm gonna explain the test. All right. So before I go back to that, right? So the secondary alcohols which contain this group, all right? This is the group we're looking at, Even let me see. Let me draw the group. All right. This is the group we're looking at. This group must be present. If this group not present, reaction naga. It will never happen. Right? And this is interesting. If this group isn't present, this reaction will not happen. Right? So in secondary alcohols, of course this group will be present because it could continue with other R groups off here. And in ethanol as well, in ethanol, this is why ethanol reacts with it as well. Because ethanol has this structure, right? Ethanol has this type of structure, right? In which it only has a hydrogen right there. So it can happen with ethanol and it can happen with secondary alcohols, but it can't happen with any other primary alcohol or tertiary, right? So that group itself, right, is oxidized by iodine in the presence of sodium hydroxide, right? Remember what I said about Unit 2 chemistry. Write down the reaction, write down the reagent, write down the condition, write down all the answers, and if it has a color change, write down the color change, right? Those are all the things you need to know. So it's oxidized by iodine in the presence of sodium hydroxide. So all I'm hearing is that the reagent is iodine and the condition is an alkaline medium, which is usually sodium hydroxide. The triiodomethane formed precipitates, right, as yellow crystals, right? So sometimes they're really dirty brown. That's because things happen, right? But usually you want yellow crystals, right? This is known as the iodoform test. One primary alcohol, which is ethanol, right, can react, which also contains that group that we have up there on the screen, and it also gives a positive test for this reaction, right? So these are the yellow crystals we want to look at. Let me move this a little bit more and increase the size of this. So you can see the yellow crystals that we want to be forming there. So we need those yellow crystals to be formed. This is the triiodomethane that we're looking at. All right. And triiodomethane, we know how it looks already. Right? Because we're going to have iodine, iodine, iodine. Right? It's going to precipitate out a solution because the large atomic large atomic radius of the iodine, right, prevents for types of bonding, right, to come in. It prevents the hydrogen bonding, so it will eventually fall out of solution, right? So it's important to note this. Secondary alcohols undergo a positive test, right, for the iodoform test, right? A positive iodoform test, forming a yellow precipitate if a CH group is present next, say on the same carbon where the hydroxyl group is present must be clear, right? This can also happen in only one primary alcohol, which is ethanol. It will never happen in any other, right? But question, never mind, let me not ask that. Moving on, let me not ask that as yet, right? Tertiary, right, have no reaction at all, right? So this is general reaction here. So we have an example reaction down here on the bottom of the screen here, where we're having this reaction, well, this alcohol here reacting with our iodine and our sodium hydroxide, producing triiodomethane, right? And then we have our, I'm not sure who can tell me what this is, our acyl alkali. We have an acyl alkali being created, right? And then we end up with a sodium iodide and we end up with water, right? The triiodomethane, which is iodoform, which is created. That is what drops out a solution. That is what is the yellow precipitate, right? So the triiodomethane or the iodoform, which is produced, right? So it's sometimes we call it I call it the iodo test, but it's iodoform test. That makes sense because the product is iodoform, right? Or try iodomethane. All right. So that is that. Are there any issues or questions again? For the person who asked me to go over it, is it necessary?
No, sir.
All right. If it's necessary, now you let me know. Come, we'll go over it again and again and again. So this is generally what we have for our iodoform test. All right. Let me see if there are any issues or any questions to the chat. All right. I'm not say anything. All right. So that is that. The Lucas test, right? Zinc chloride in the presence of protons, right? Acidic solution. So zinc chloride, right? And hydrogen chloride tend to be used, all right? This is interesting though. Really, really interesting reaction. I think if you guys remember that common ion effect that will have an effect on whether or not the reaction can occur. That's why we use the hydrogen chloride or the hydrochloric acid. But you guys know common ion effect from solubility product in module 1 of unit 1. So let's move on. All right. Primary, right, alcohols will have no observable change. Secondary alcohols will form a white precipitate within 5 to 10 minutes, so it slowly forms a white precipitate. And tertiary alcohols find well forms a white precipitate immediately, right? So it immediately shoots up, right, as a white precipitate. So we have this here, right? The reaction occurs via the formation of a carbocation intermediate, right? So second, um, the secondary one, right, and the tertiary alcohols can go through this, right? Primary key I'll go through it, but we'll understand the type of mechanism, right? Because we're going to be looking at halogen alkanes, right? That kind of clears up why this happens here and why we're talking about intermediates, right? But let's just look at this. So the tertiary alcohol forms a tertiary carbocation, which is most stable, hence most likely to occur, right? Since the primary carbocation formed from a primary alcohol is not stabilized, it will not undergo this substitution reaction, right? So the substitution reaction that we're looking for here will not be taken up by primary alcohols, right? Secondary alcohols tend to have this type of substitution in which it forms intermediates, and the first step tends to be the rate determining step, which is the slow step, right? And then the tertiary one will just have one immediate reaction, right, which is concerted, which means it lacks an intermediate in a sense, right? So it has that there. So in this reaction here, we have this picture here where we have a um slightly turbid mixture here, right? So this is a secondary alcohol, right? Because the white precipitate is forming over time, right? And then the tertiary alcohol would be the one that has the immediate cloudy effect, right? The white precipitate. Primary will not give anything. All right, so that is the difference between the three, right, types of alcohols or classifications of alcohols on the Lucas test. All right, so that is it. Are there any questions or concerns with the Lucas test? Any issues? Any concerns?
No.
Can this be, sir? Are you gonna? Sir, is this being recorded?
Um, most definitely.
Okay.
Why did you ask?
Sir, cause even though like your brain there, but not there.
LOL. All right, that's understandable. All right, so that is it. Right, so the Lucas test. Right, we need to know that. And Lucas reagent is zinc chloride in the presence of hydrochloric acid. All right. So let's have a look at this. Reactions of alcohols with carboxylic acids. Right. So alcohols will react with carboxylic acids to form esters. And this reaction is catalyzed by sulfuric acid. It is reversible and it is carried out under reflux. So we should know this. Esterification is the name of the game here, right? So we have esterification here. All right, so carboxylic acid plus alcohol. It is also a hydrolysis reaction, right? So it produces water, right? Well, I wouldn't say hydrolysis, sorry about that. It's not a hydrolysis reaction, it's a condensation reaction. My bad. Because it produces a smaller byproduct, and in this case, it is water, all right? So we have that, the creation of the ester. Dehydration of alcohols now. Alcohols which have at least one hydrogen atom on the carbon atom next to the hydrogen hydroxyl group reacts with excess concentrated sulfuric acid on heating to form alkenes. Right? What is this talking about? We're saying that Alcohols that have one hydrogen atom on the carbon next to the hydroxyl group will form alkenes under heating with concentrated sulfuric acid. What we're talking about here, right? What are we talking about here? Not sure what we can talk about here. The classification. And I want you guys to tell me what classification of alcohols it's referring to. Notice I didn't just drop up a classification. I want you guys to figure it out. Right? You could just drop it in the chat. Alcohols are dehydrated to the corresponding alkene using concentrated sulfuric acid, or we can use phosphoric acid, right? And we can also have this type, this aluminium trioxide, right? So let's have a look at this. Ethanol within the presence of sulfuric acid under a certain temperature around 180 degrees Celsius. It needs to be over boiling point generally. With excess acid will give us ethylene or what we call ethene, and it will give us also water. All right. So we can convert the ethanol back to an a ethene, right? And we looked at the reactions of alkenes before this, and we know that we can hydrate the ethene back to ethanol, right? So we unlocked a little reaction pathway there, right? We can find different reactions that can reverse the effects, right? So the dehydration of alcohols can be reversed by the hydration of the corresponding alkene, right? Any issues here though? Any issues?
Or could you repeat the last statement that you said?
Okay. So what I'm saying is that we can reverse these reactions, right? As we go through organic chemistry, we're going to find reactions that are reverses of, are opposites of themselves. So when we dehydrate alcohols, what we're doing is removing water from the alcohol, right, to produce the water itself from the alcohol to produce an alkene. But as remember from the reactions of alkenes, we add water to get back an alcohol. So it's a reverse reaction would be the hydration, right, of the alkene. So reverse would be hydration of the alkene to get back the corresponding alcohol. Alright? So that is what I'm saying. Okay? Are there any issues there?
Yes, sir.
Okay. Alright. Any issues? Any concerns? Can you guys drop a one in the chat if everybody's following so far? So if you're following, everything is fine. Just drop a one in the chat before I move on. Just let me know that everything is fine. Okay. So Faith, Arifa, Joel, Jardina, Nicholas, everything is fine. Seeing one from all of them, but all right. So let's have some practice here now. Da 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 da. Identify which of the products, all right, formed from the dehydration of 2-methyl-2-butanol is the major product and which is a minor product, and explain the reason for your answer. So here we have the dehydration of 2-methyl-1-butene, right, and 2-methyl-2-butene. So the dehydration will give us 2-methyl-1-butene and 2-methyl-2-butene. So these are two products that we can form. Which one is the major product and why? Anybody let me know. Anybody can let me know what is the major product and why?
So 2-methyl 2-butene.
For the
Okay,
second,
why is that? Okay, give him a second. Let me
yeah,
hear what he has to
because
say first.
Alright, so in dehydration, the 2-methyl 2-butanol, we are going to create a carbon cation because essentially, really and truly, we're going to remove the OH group. And the most stable carbon cation that will be formed is the one with with two. So in that
Secondary?
sense, yeah, the secondary that.
Mm-hmm.
So in that sense, when that is formed, electrons will flow from one of the H bond CH bonds into to basically neutralize that carbon cation and form the double bond. So I think that's why the two butene will be formed.
Okay.
Methyl butene.
2-methyl-2-butene. All right. Are there any conflicting answers, or do we agree? Do you guys agree with his answer of 2-methyl-2-butene being the major product based off of carbocation stability? If nobody agrees, then we're just moving on. All right. I think the answer was fine. All right, for 2-methyl-2-butene to be the more stable one. Um, 2-methyl-1-butene actually would actually be produced by the more unstable intermediate. Therefore, it will occur in less amounts, right? In a smaller ratio, right? So 2-methyl-2-butene is the more stable one. And how do we know the stability of these products? One of the ways we can look at it is through the substitution, right? This is a monosubstituted thing, and this is disubstituted, meaning that it has more groups at the end of the different bonds, right? So at the end of this double bond, we have two alkyl groups, right? And then we do have another alkyl group there. At the ends of these double bonds, we have two alkyl groups here, and we have another alkyl group. This is more stable, all right? That's a way to look at it as well, all right? So that's generally it. So this will be the major product over this being the minor product, right? And when you go to higher chemistry, you're gonna talk about Zaitsev and Hoffman products, right? Right, and seeing how which one is the more stable one, which is the more major product and stuff like that. But that this is basically a prelude to that, right? So that's really it. And we have the production of water as well because it is a condensation reaction, right? So we have that. So we have another thing, right? Draw and name all the isomers that can be produced when 3-methylhexane 3-ol is dehydrated and state the relationship between and the two pairs of the isomers, right? Let me see. Let me see. Let me see that. Let me see that. Let me see that. I probably wrote the wrong answer there. State the relationship between two pairs of the isomers, right? So let's look at this. Can you guys dehydrate that for me and let me know what the answers are? Right, that is the last part of this entire thing. Right, this is just a summary at the end. So this is the last thing. All right, just draw. In the interest of time, just try the first bulletin. You can try the next one, stating a relationship between the isomers on your own. All right, but draw and name all the isomers that can be formed when 3-methyl hexane 3-ol is dehydrated. All right, I'm gonna give you guys some time for that, and you should be fine otherwise. All right, so that's it.